Okay, our next speaker will be Chen Chen, and he'll be talking about a path-hidden lightweight anonymity protocol, the network layer.
Thank you. Thanks for the introduction. I'm Chen Chen from Carnegie Mellon University. Today I'm going to present my work, PHI, Path-Hiden lightweight anonymity protocol at network layer. This is a joint work with my advisor, Adrian Perrick from ETH Zurich. To start, let us look at the general picture of anonymity protocols today. We observe a trade-off between security and performance. In the middle, there is Tor, which is the most popular anonymity protocol, and it provides bitwise unlinkability for security and provides around 100 megabits per second throughput. There's another side of research which aim for traffic analysis resistance and defend against stronger attackers. And this type of protocols usually provide a lower throughput, and people applaud if they have 30 seconds end-to-end latency. And on the other hand, there's a new line of research about lightweight anonymity protocols. Their main goal is to hide the forwarding paths taken by the senders and try to anonymize the user, therefore anonymize the users. And their performance is usually around 100 gigabits per second. So if we compare the literature size of different anonymity protocols to the astronomical bodies, so I would say the literature size of Tor-related work is like Jupiter, and traffic analysis resistant related work is literature size comparable to the Satan. And where is the lightweight anonymity protocol? Well, somewhere there. There's a star, believe me. But what I try to say is, I mean, the size should be big, but you just cannot see it right now. So now here in this work, I try to expand that literature size and focus on the lightweight anonymity protocols. Basically, I want to strengthen three features of this type of protocols. First, it should provide high speed. By this high speed, we're talking about 100 gigabits per second packet forwarding. And second, it should provide high scalability. So by design, there is usually no per flow state on each router. And finally, this type of anonymity protocols are deeply incorporated into network architectures. To understand lightweight anonymity protocols in detail, let us together look at the LAP, which is the first protocol in this line of research. Suppose a client S wants to communicate with destination D anonymously. And this is the toy topology they were using. And the goal of LAP is try to hide the path taken by the source and to reach destination. And the key idea is that each packet carries an encrypted header that contains the routing information. And for anonymity, each AS has access only to the forwarding information of its own in the packet header. Okay, let me use this example to explain how the encrypted header is built. At the beginning of the connection, the source will send out empty packet, setup packet, that contains the destination address. So each AS can independently determine how to forward a packet given the destination address. For example, AS3 knows to forward a packet to AS1 if it sees destination. We also assume that each AS has a local secret key. And to process the packet, AS6, for example, will first compute encrypted the forwarding information, that is AS6 to AS3, using its local secret key, key 6, and then add a MAC for the ciphertext. After that, AS6 will put both the ciphertext and the MAC together into the packet header. And this combination of these two fields, we call it a segment. And the same goes on with AS3. The only difference is that when computing the MAC, AS3 append to the ciphertext the segment of AS6 as 6. So as you can see, when AS9 put down its own segment into the packet header, so the packet header contains all the encrypted forwarding information required to forward a packet. So thus, this packet header can be put in each data packet. So when processing a data packet, each AS will only do one symmetric decryption to retrieve its forwarding information and forward a packet. But there is one problem for LAP. That is, in this case, AS6, which is the first hop AS, knows both the source and the destination. which harms anonymity. And as the famous David Wheeler quote, all problems in computer science can be solved by adding another level of indirection. So Dovetail, which extend lab, try to hide the destination by adding an indirection. Specifically, Dovetail, in Dovetail, the source pick another node called hyper node to help set up this path to destination without leaking the destination address to the first hop AS. And this is how it do it. The source will first encrypt, pick a hypernode, and then encrypt the destination address using the public key of the hypernode. And then the source will extend the blue path to the helper. The helper can decrypt the message and retrieve the source destination address. And then the helper is supposedly to extend another path, the right path, to the destination. So the AS node at the intersection of both paths is called the tail node. And tail node is responsible to form the final path, which is the green path. As you can see in this way, so no AS will know both the source and destination at the same time. So here's a brief comparison between Dovetail and LAP. So Dovetail prevents any AS from knowing both source and destination, and which means better security than LAP. However, to use this fancy Dovetail setup, the source has to control the forwarding path and select the Dovetail node, which is not always possible in all network architectures. For example, in the internet, the source has little control over the forwarding path. Therefore, this cannot be used with internet. So our question is, how do we achieve best of both worlds? Meaning, how do we have better security and hide the knowledge of both source and destination from any AS, and also make the protocol work with the internet? And before I proceed, there's indeed one more problem. That is, both the LAP and Dovetail's packet format leak AS position information. For example, in this case, let's assume AS9 is adversary, and then by its physical position, it knows destination because it's the last hop, AS. And by looking at the header, it sees 5 AS segments before its own segment. That means it's the 6th hop AS. So if you further look at the topology, it sees the AS6 in this topology is the only AS that is 5 hop away. That means the sender must be in AS6, which greatly reduced the sender anonymity size. So when we envision this new protocol, so we want to have better anonymity and compatibility. For better anonymity, we mean that the packet header format should not leak AS information, position information, and also the path setup should prevent NAS from knowing both source and destination. And finally, it should be compatible with internet and should work without the source to control the forwarding path. So we propose PHI, which is short for Path-Hiden lightweight anonymity protocol. So it proposed 2 new techniques. The first one is segment position randomization. It's essentially a new way to compose packet headers without leaking AS information, AS position information. The second technique is back-off path setup. This is a path setup method that improves over Tor's path setup and make it work with the internet. I will introduce them one after the other. First, let us look at segment position randomization. So the key idea is to randomize the position to insert a segment. So each AS will use a pseudo-random number generator keyed by its local secret key, and then compute a pseudo-random position to insert a segment using the session ID. For example, AS6 will compute a position, let's say 3, and insert a segment at the position 3 in the header, which is, and AS3 may compute a position 2 and insert a segment at position 2. So you can see that's how it goes on. And essentially, this technique breaks the correlations between the segment's position in the header and AS position along the path. That's how it hides AS position. You may be wondering what happens if 2 AS compute the same position. Then we have a collision. For example, let's say AS6 and AS1, they both computed position 3. So in this case, AS1, by inserting its own segment, will override the segment written by AS6. The resulting header cannot be used. So this is a problem. In the paper, we talk about 2 techniques. to avoid collision and improve the success rate. The first one is to have a larger header, obviously. So we talk about have up to 12 segments needed for on average 4 hop plus. And this improves the probability, but still for each setup packet, so it has a probability of failure. So in the second technique, we propose the sender to send multiple setup requests to enhance the probability of success in the setup phase. So you can, we have evaluated the performance overhead and the corresponding success rate in the paper. So briefly, so to achieve a 99.7 success rate, so we only add minimum overhead over the existing protocols. Okay, now let's talk about backup path setup. So essentially, the beginning of the backup path setup is the same as Dovetail, meaning that the source will establish a blue path to a hypernode and secretly deliver the destination address. And now here's come the difference. Instead of let the hypernode to extend a different path, so the hypernode will enter a backup path in which the hypernode will send the setup packets along the blue that traverse the blue path in the reverse order. So for each AS on the path, it will independently check whether it can forward the packet to destination without following the previous blue path. And also, it should check whether this forwarding will violate its forwarding position. So the resulting AS is called a midway node. And let's assume in this example, AS1 is the midway node. So it will extend the right path to destination, and then form the green path. So compared to Dovetail's path setup, so in this backup path setup, each AS independently determines and make decisions about whether to become a midway node or not. And AS no longer needs to control which node is the tail node. And therefore, we remove the requirement to control the forwarding path for the source. Okay, so we evaluate the anonymity set size of phi compared to LAP and Dovetail. So the figure shows the cumulative distribution function of anonymity set size for the 3 protocols. The 2 lines to the left shows the CDF of the anonymity set size when an authority receives a packet from its customer or peer. And the right 2 lines shows the CDF anonymity set size when an authority receives a packet from its providers. So we can see for each pair of these 2 lines, we can observe a gap between roughly 2 to 10 between the 2 sides of protocols. So that size, roughly speaking, Phi's anonymity set size is up to 1,000 times larger than LAP and Dovetail. So there is indeed more in the paper, which we can now cover in this talk. For example, we talk about variable size segment technique that is used by LAP and Dovetail to hide AS position. And we quantitatively shows why it fails. And in addition, we talk about how to bind data encryption with the path setup. And we propose a strategy called probabilistic header size that help reduce the header overhead. And finally, we present the implementation of Phi and show more evaluation results for its performance. So since the paper is published, so we indeed receive emails, and one of them, George Becker, successfully proposed some passive and active attacks that help leak information from a randomized, from a header that built by this segment position randomizations. So for the passive attacks, on-pass AS can actually compare a setup header with the data header to learn more information about the distance to destination. And for active attacks, so on-pass AS can actually modify the segments in the header and then send the packet, follow the path to see whether the packet goes through, so to learn AS position information. So currently we are working on a protocol to fix these attacks. To conclude, so in this talk I propose Phi, Path-Hiden lightweight anonymity protocols, which essentially a combination of 2 techniques. The first one is the segment position randomizations, which is a way to compose headers without leaking ASC information. The second is back-off path setup, which is a new way that improves Dovetail's path setup and make it work with the internet. So with that, I want to end this talk, and I would like to answer your questions. Thank you.